Hello, this is Ertan Teskin from Ozan Engineering. In this video, I'll be demonstrating a method on modeling of numerical dye washout with scalar transport equation in NCCFX. It is a case study of blood flow through aortic arch. Blood is not an ordinary liquid. Therefore, uninterrupted streamlined flow is critical for medical device applications due to a potential of thrombus formation because of flow stasis. It is a residence time investigation method which numerically models dye washout using scalar transport equation. Let me give you a bit more information about the application. So this method has recently been introduced to perform ventricular assist device specific washout investigation. And the method relies on solving a scalar transport equation where the scalar demonstrates the dispersion of the dye. The dye concentration, shown with a capital C here, was modeled solving a convection diffusion reaction equation. And in here, diffusion and reaction terms are zero. The fluid domain needs to be initialized with a dye concentration value of 1, while the inlet dye concentration value should be 0. During the transient simulations, the dye from the inlet would be advected to the flow domain. The details of the model geometry and the flow conditions are shown here. First of all, the image indicates the aortic arch geometry with anastomosed ventricular outflow graft, which is an inlet to this model. And the outlets are the 3 branches as well as the main outlet. The mass flow inlet condition was applied here for a corresponding volumetric flow rate of 5 liters per minute, which is a typical VAD flow. For the branches, again, mass flow outlet is applied with 20%, 10%, and 10% of the flows at the inlet for the branches 1, 2, and 3 respectively. The pressure outlet condition was used for the main outlet. For the setup, we utilize the workbench environment where the different modules are actually utilized. Let me continue from the model here. As you see, the different components are also shown here: geometry and mesh, steady state CFX, as well as transient CFX. The mesh actually transferred to the setup of the steady state module as well as to the setup of the transient module. But the results of the steady state run is also utilized as an input to the transient simulation. So let me briefly show you how the geometry looks. Its geometry is actually generated with the space claim here. Inlet and outlets are here. Corresponding mesh with some prism layers there. But don't forget, in many other applications, finer mesh as well as multiple prism layers might be needed. This is, if we go back to the steady state CFX, this is the pre-processing screen where the inlets and outlets are actually specified with the arrows here. As I mentioned, this is an application of a scalar transport equation. So we have to turn the additional variables on and define a volumetric scalar. And we should also define a transport equation in the fluid models section of the default domain. Lastly, we should generate a subdomain with the corresponding flow domain, and then go to the sources and define 0 here. We can control the simulation results with certain outflow controls, such as the velocities on different regions, as we like to do. while running the simulation, steady-state simulation, the fluids and the turbulence are solved. However, the scalar transport is not activated yet. The steady-state results are shown here. As you see, this is the inlet section where the higher velocity actually enters and hits the aortic arch, and some portions, as we defined here, are actually leaving the flow domain from the branches, and also some of them are actually from the main outlet region. So if we go back to the transient setting, so we will see that in this time the analysis type is transient, and we can define the total time and the time steps depending on how the model settings are. And when we go to the expert parameters, to the model overrides, now you see the scalar transport equation will be solved, including the fluids and the turbulence. And with that, the results are obtained. So results could be demonstrated in different forms, such as the concentration profiles, as shown here. As you see, these are the three different branches, as it is mentioned before. And for a while, during a simulation, it's about a second or so, and nothing happens. But after the flow is actually advected towards the branches, and then we start to see the impact of the inlet dye reaching to the outlet regions, and it actually in time gradually reduces down. Here are the results of the transient simulation. On the screen, the dye concentration contour is shown at the last time point of the calculation. Opening the animation window and bringing the time to the beginning of the simulation at time equals 0. As you see, the scalar quantity was set to 1. Throughout the iterations, when the time advances, the dye concentration changes and the dye distribution also changes. So this method could be a helpful tool to make a comparative analysis and can be implemented to any problem where the residence time is an important parameter. In this case, it is demonstrated on an aortic arch with a blood flow. However, it can be applied to any medical device associated with blood flow at many different settings. Thank you for watching.